All right, let's do something here. That's done, like chicken. Excellent. It tells me it's all going like chicken here. Let's get rid of this. And let's bring up the data I'm talking about. All right, first, before I start talking, let's see what we're doing here. Oh, my God, yes. Now, bring up the data I'm talking about. Right, first, before I start talking, let's see what we're doing here. Oh, okay, so I'm just trying to get through all the teething problems as it relates to live stream, and it's a bit of a pain in the ass. I have two computers working here, one so I can see what the heck is happening on the screen, and the other one is actually live screen. And here you're looking at my actual data set. This is the source. My name is Gordon MacLeod. I'm a pseudo-astronomer. Let me get that off. Okay, so I'm a pseudo-astronomer. I don't know if I ever describe myself as. I'm a presently unemployed astronomer. Let me say it like that. I am a presently unemployed, I'm between contracts. It's probably a nicer way to say it, isn't it? But anyways, and I'm sitting here in beautiful central Alberta. It's probably 10, 15 Celsius right now outside. It's sunny skies, a bit of cloud. Hope to see a moose or two today, but I doubt I will, because they tend to go into the bush where they can get lots of food right now, because there's no snow. So just so you know, that's how it works out in the world of where I live. I'm on my brother's ranch. I actually do a lot of the I wouldn't say animal husbandry. We used to do that, but we've gotten rid of that. Now I just take care of the trails, basically, while I make these videos. And today I just want to talk about some crazy science, and you're looking at that. So you can see here I've got an Excel spreadsheet. I do most things in Excel. It's because I spent 20 years in business. After leaving astronomy in 1996, I did an MBA, or rather I went to Mexico and then I decided to do an MBA. And afterwards I ran businesses for several years in Southern Africa, and I wound up in really exotic places. Okay, mostly in South Africa, but I ended up in places like Angola, Luanda, Angola. Now there's a snake charmer of a life existence. I remember, and this is an aside, I'll go into the video for a second, but just to give you an idea, I remember saying that, well, I can spend 6 months on my head in a septic tank because of my upbringing and whatnot. At least I thought that way. And then I moved to Luanda and I realized I actually was living in a septic tank. Now, that's being unkind to the Luandans. They're incredibly great people. Angola itself is a really great place. It's very harsh, very difficult, incredible amounts of poverty. But the city itself is literally covered in a layer of human feces. And that's the nicest way I can put it. Because when the city rains, the city doesn't rain. When it rains on the city of Luanda, which is a port, just doesn't matter, of course, it's shaped like a bowl, and the drainage systems in the city no longer function or haven't functioned for many years, largely because the city was built for 500,000 and now about 7 million people live there. So the traffic is unbelievable. When I was there in the 90s, or early 2000, there was only two stop signs or two stoplights, one robot. Literally, it was a giant robot that directed traffic in the center of town. It was really a hellscape. I mean, there was a building where they had killed the previous presidents. The leader of the one rebel group was wiped out by the other ones. They set up 50 cal machine guns across the building where he had his offices, and they literally just peppered the building with 50 cal machine guns. It went straight through the building. You can imagine the carnage. They took the bodies out into the bush, and then they said they took photos of it, and they put it onto the world and said how they had captured and killed the leader of the resistance movement. You can play the politics any way you like. It was terrible. But the city itself did not drain. And so it just simply had this, when it rained, it flooded, and then you had human feces floating everywhere. And if you think you can walk out of that when the water's 4 or 5 feet deep, you'd be surprised. The answer is no, because there are no manhole covers. A lot of them are missing, stolen, whatever, and you end up falling into something that you don't want to fall into. So I was trapped in my house actually for 2 days on the second floor. We had no power, and my buddy and I just sat around, played chess and checkers and talked shit all day. That was Luanda. I was there for 6 months. Then I got kicked out of the country. They were going to take me and throw me in prison, actually. It wasn't so much I was kicked out of the country. There's no doubt I had to leave. The police arrived at our offices, and I was being arrested and to be taken to jail for working illegally in the country. And of course, that didn't make any sense. But that's what makes sense, and what people describe as legal is very different in places where it's quite autocratic. So I was in the middle of something, all in different languages. Okay, my Portuguese is terrible, and basically my friends ended up having to hand money under a table to these 2 police officers to get them to allow me, so they could go away, so that I could then get on a plane the next day and get the hell out of the country before going to prison. And then, so I was basically told to leave. I left. And I wound up at the airport realizing and this is actually important to what we're doing today. I wouldn't be doing this data today had it not been for what happened to me in Luanda, Angola. I mean, I was happily running businesses in Southern Africa and making a living at it. Sometimes the living wasn't very good, but generally speaking, I was doing okay. And I was sitting at the airport, and I remember sitting there thinking to myself, how the hell do I get myself into this shit? Like, I almost went to prison. In an African prisons, in these places, you can imagine the worst, and it's worse than that. Okay? People die in these places. I mean, regular. And for a person like me to get in there, it's not going to be good. Okay, I'm used to harsh living, but that's going to kill me, most likely. And I remember sitting there, and I got my phone here, and I'm going to use it as a prop. I remember thinking to myself, how the hell do I get into this? And the answer is because I keep answering this stupid thing, my cell phone. And so when I stopped answering my cell phone, my headaches went away. What I decided was, at that day, at the airport in Luanda, waiting to get the hell out of that country, I decided that this is, it's not worth it. It's just not worth it. I mean, my trajectory was always going to be into very difficult places where I had to make the hardest decisions possible. I was literally hired to fire people in places where nobody else would go. So they would send me into in Luanda, Angola. And I would be there, and my job was to resuscitate a factory, that hadn't operated. Well, it was still operating, but it needed to be repaired. And it had literally bullet holes coming down into it from the South African Defense Forces that was fighting against the Angolan forces, and it had bullet holes going up through the ceiling, if you could imagine. I had machine guns in my desk. I had AK-47s in my desk. That's where I worked, and I was there for 6 months. It was, and they wanted me to wear pants. It was 40 Celsius, and I'm sweating my ass off. We got no power because the power is intermittent, and that's the kindest way to say the power supply was. What it was is, if we had money for diesel, we could run generators to operate the factory. Without the diesel we couldn't operate, and therefore we had no power, and you had no water, no power, no nothing, and you had to be there. It was a hellscape. It really was. But the people themselves I met there, a lot of them are really good people, really hardworking. A couple of the people that I worked with, who I was trying to get them to do something, actually, they turned me into the Department of Labor, who then sent the police to have me arrested, in turn leading to my partners putting money under the table. It's about $1,000. I don't think it was a hell of a lot. I'm not worth that much. Just I'm worth $1,000. Okay, so there's a price to me, and I'm worth $1,000. Not worth much more than that. And I've been in other situations where I'm worth even less. Like I was caught in a diamond scam in South Africa. I was worth $100 to get out of that, just so you can imagine. So I've lived a rather checkered life. But sitting at that airport in Luanda, I had decided I'm going back into what I know and enjoy, and that's big tech. So that basically meant going back into the astronomy sphere. And if that meant, getting involved in, just doing basic astronomy, and fortunately for me, there came upon a job where I could work for the South African government in the bid to host the Square Kilometre Array. And I did that for a few years. And then I went into other big projects in Southern Africa and eventually back into astronomy. Now here I sit in Alberta between contracts. So that's the history behind this data set. Because without that, I wouldn't be sitting here today talking to you about this data set. Just to give you an idea. So remember, astronomy is not just astronomy. It just isn't. You're fortunate if you get a job at a university somewhere where you're teaching students and you're doing your research and you got a balance. You go home to your family or whatever your situation is, you can park off and relax and do things. You're lucky if that's the case. And the vast majority of people in this field of astronomy, once they've gotten that job and that security, are able to do that. But if you're one of these people that live in postdocs all your life, then the answer is no, that's not going to be the case. And basically, I was in the latter category, mostly because I wanted to go work in places where, and I honestly did. I took myself to South Africa. I set criteria when I graduated from my PhD. I applied for jobs in Ireland and the United States and various places. There's some issues I would have to go through to get a job in the United States. That's not a story. I'm not going to go into detail. You can imagine. It's from my family and my past, my youth mostly, which I kind of grew out of. But basically, you could go into the field of astronomy, and in my case, I wanted to go to a place in the Southern Hemisphere where I could look at most of my sources. So my criteria was very simple. Find a country that did radio astronomy and was in the Southern Hemisphere. And then the third criteria was played rugby. So I had three criteria with which I used to look for jobs. And there was only two countries in the Southern Hemisphere that did astronomy, and they were South Africa and Australia. And I didn't even know about South Africa, to be honest with you, in terms of radio. There are other places, of course, where they do radio. I didn't know about Fortaleza in Brazil at the time, things like that, but I learned about them after I got there. So, anyways, that is what got me to here, just so you can imagine. And that's the career path that I wound up in. But fortunately for me, I got to go back to Hartrail and help resuscitate their spectroscopy program, which included this source. Okay? While at Hartrail, of course, I just went back to just processing my original data and getting stuff out of that, publications and whatnot. And I had always wondered, in this particular source, and this source is called G9.62 plus 0.2 E. And there's a whole bunch of star-forming regions in and around this source, but this particular source is interesting because it is the brightest methanol maser in the galaxy. Now, let me put my glasses on so I can see what the hell I'm looking at. And let's see if I can give you, do I have anything in here that would resemble a spectra? I don't know, I'm just going to try to show you something here. Let's see if I can do, let's go up to the very top. And of course, probably not. Oh, there it is. Okay, so here we go. So this is the brightest methanol maser. This was called the mother of all methanol masers in the 1992 methanol masers conference. So the inaugural masers conference was held in Washington, D.C. in 1992, and I attended it. It's one of the few conferences I've actually attended. I'm not a big fan of conferences, mostly because I don't like talking in public, and here I am talking on a video. But anyways, this was discovered by Carl Menton, a great researcher and a real treasure to astronomy. Out of Germany, he was probably, I think he was using this particular, this is our data from Hartrail, but he was probably using the 44 meter or the 42 meter that's in Greenbank at the time. Okay, it was pre, it may be the 300 foot for all I know, but it was pre the GBT, pre-GBT, okay? 1991, he did the observations and he presented them and published them, and then he talked about them in 92 at the conference. And then I saw him again at my only second time I've gone to this conference was in 2017, and that's only the second time he and I ever chatted. He's just such a great guy. Really, 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 really good astronomer, really astute, really knows his stuff, right? Especially masers. He really has a finger on them. He really has an understanding of how they operate. And if you ever get a chance to read interesting papers, his papers are them. Mine, whatever. I'm not going to say anything. Anyways, so this is the spectra of the source. And what I mean by spectra, for those who don't do astronomy and think I'm just talking BS science, this is it's like, it's in spectroscopy. If you're doing an analysis of gases, if you're working in a hospital and you're doing an analysis of blood work and stuff like that, you'll get spectrographic graphs like this. And we put it in terms of velocity because we've tuned the telescope to the specific frequency of this transition for this molecule, which is methanol. Okay, so we've tuned it to 6.7 gigahertz. It's actually 6.6685, blah, 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 all sorts of numbers. So you want to be very accurate. And then, of course, you got to correct for the Earth's motion around the sun, which, by the way, I have not done to this data. We've corrected for the Earth's motion around the sun, but not for the planets. And that's for another day. That's something I'm working on that's even sillier, but you'll see a bit of that in this data I'm going to show you. Okay, so this is the spectra. That's what it is, to give you some background. If you're in chemistry, you'll be doing spectroscopic analysis of gases, and from that analysis, you'll be able to determine the different gases or chemicals that's in your sample, right? Well, ours is basically the same, except here we're finding what we call masers, which is basically it's a laser, but it's microwave radio waves. It's microwave wavelengths rather than optical wavelengths, okay? So laser is light amplified simulated emission, blah, blah, blah. I can never remember the exact thing. I really don't care. Whereas mine is masers, M-A-S-E-R, okay? Anyway, so these are masers. And around star forming regions, massive star forming regions, things, if I'm looking out the window, I can see the sun. That's one solar mass by definition because it's the sun. And these objects here will be greater than 3 solar masses or 4 solar masses. So they have to be big enough that they can energize the surrounding gases and create what we call an H2 region, which is basically a region of hot electrons, about 10,000 Celsius, that then radiates in the radio emission. It's a thermal spectrum that's in the radio. So it's in infrared, but we see it in the radio, and it acts as a seed photons for things like this. Methanol masers. Okay, so you have a star forming region where you have a star greater than 3 times the mass of our sun, and then it creates a energized electron gas field around it, plasma of 10,000 Celsius, Kelvin, whatever, and that then radiates outwards and towards us radio waves that are basically photons at radio wavelengths, and they cause the energized methanol masers, the energized methanol transitions to cascade down and give us these transitions, which gives us these lovely masers here. So this is a maser, and that maser is comprised of multiple features. In a spectrum, you know, you get lucky and it'll be one dominant feature will be the majority of this 6,000 Janskys. Carl Jansky created radio astronomy back in the 1930s, tried to publish an astronomy journal, and they rejected it because they didn't believe there was any way that you could detect radio waves from astronomical sources. It was one of the greatest tragedies of astronomy. The Astronomical Journal rejected the paper by Carl Jansky in the 1936, something like that, because they didn't believe that it was possible. So it took to the 50s for them to start recognizing that radio astronomy, in fact, was astronomy. And for a very long time, there was not an animosity, but there was an undercurrent between the two factions, those who did radio and those who did optical. My supervisor was one of the original radio astronomers, and he was being taught in Manchester, basically one of the big radio astronomy communities at the time, and he was an electrical engineer. So everybody saw radio astronomy as electrical engineering and not real astronomy. Anyways, Karl Jansky, of course, shrugged it all off and published his work in IEEE, an engineering paper, and thought nothing of it, went about his career, and eventually was given the credit he deserved years later, 20, 30 years later. And that's how science goes. But anyways, so this is a maser, and this is towards star-forming regions, and we only see these masers towards star-forming regions, only. So massive star-forming regions have these types of masers at this transition of 6.7 gigahertz. Okay? So there we are. That's the first and foremost part of it. Anyways, but this is the prototypical methanol maser, because in 91, as I was saying about my good friend and great astronomer Karl Jansky, I will call him a friend. We don't know each other that well, but I would consider him one. Anyways, this was the brightest methanol maser. And at the conference in 1992, it was the beginning of the Iraq War, which they kept referring to as the mother of all wars. And this was the way it was being billed, and all of the armies of the world were getting together, and they were putting people in. And I even almost joined, to be honest with you. But he was talking about this particular source. He says, this is the mother of all methanol masers. And that was his little coined phrase at the time, which was quite catchy. And everybody had a good chuckle about it, of course, including myself. It's just so bright. I mean, really, it's about twice as bright as any of the other methanol sources there are. So the next ones around are, I can't think of what's the next brightest one. I think I can't remember. It doesn't matter. But it's like 4 or 5,000. It's not 7 or 8,000. And of course, back to me being at Hart Trail the second time, Sharmila Goodhart had then came along and in 2003 stunned the world by publishing that this thing was periodic. Okay, when I say periodic, let's see if I can find you. That's not going to be it. Let's go here. This is Ibaraki, and this is the Japanese 32 meter. I've got data for Hart Trail, but let's just use this. It's on the internet so you can easily see it. And you can see the periodicity of this source in dynamic spectra. So here's that velocity. So here's velocity, and here's the strength, the flux. Well, here's the velocity, and the contours are the colors here represent the flux. And finally, so you can imagine all those spectra stacked up for all of these epochs of observation. And here we got it in MJD, and at the top you can see it in years. MJD is modified Julian days, for those who don't know. And you can see the periodicity. So every 240 days, this thing would vary. And of course, if you've looked at some of my other videos, I found a feature in here in the what looks like noise, because you can't see anything, but when you do it in logarithmic scale, you can see a second period of 51 days here. And that was another astounding thing. So not only is this the brightest maser in the galaxy at this transition, it's periodic, so it's the prototypical methanol maser, it's the prototypical periodic methanol maser, and now it's the prototypical 2 periods maser. And worse, more importantly, it also has velocity drift. You can barely see it here. You can barely see it here. You see it down here. Oh, geez, I'm not even going to be able to show it. This graph is terrible. I really wish they had the logarithmic scale. It just was much better. Anyways, but all of these features down here are blue shifting, and all the ones that you can't really see, you can only barely make out, are red shifting, are up here. So as I said, those are terrible. Well, I can show you a picture of that. So this source is incredibly interesting and powerful. So not, like I said, it's periodic, or it's the brightest methanol maser, it's periodic, it's got velocity drift, it's got a second period. What the hell else does it have? Well, let's take a look. So while I'm here, okay, let's make this a little larger. I'm I'm going to go down to the velocity. I got all sorts of crap data, and I'll show you in a moment. Oh, here we go. Okay, so here's the velocity. So when I was telling you about this, I was talking about, what the hell am I saying here? Basically, I don't know why my screen's not doing anything here. Is it? I don't know. It doesn't matter. But you can see the velocity drift here. Is it visible? Down here you can kind of see it's falling away from -3 to -3.5. This one's a little smaller. These was here, and I fitted lines to it, so I'm fitting, I don't know, I fit lots of things here. But you can clearly see it's non-zero. So here's one, for example. It says it's got a factor of 8. It's this one here. Okay? So it is rising in flux. So if I go across, I'll probably find another one. Let's see if I can find something. Yeah, here you can see it. So here you can see this thing is rising up, and these are falling down. And that's the velocity drift that I published in, I can't remember what year it was. Who the hell knows? Who cares? But as I said, this source is incredibly interesting. And so let's see, do I have anything more here? Yeah, you can go through all sorts of stuff. This is one of the features that's velocity drifting and periodic. So it's moving away from the neutral velocity, and it's also varying, just as you can see here. So, and you can see that I do all sorts of weird, crazy things. I don't know. Don't worry. This is the time lags between the velocities. There's some features that are clearly separate from each other, lead and follow. Whatever. But here's the line widths. So you have the different features. They have the line width is broadening and narrowing as the flaring's occurring. And you might expect that. You might expect this because we're talking about as something gets brighter, it's starting to saturate. So what happens is, so basically we call it a saturation cycle. So it begins to saturate. So it goes from unsaturated, so it has exponential growth. It becomes extremely bright very quickly. Okay, that's what exponential growth. It's kind of like a viral video. When they say viral, it's the same with this. When the flare occurs, it starts off viral. So it just takes off like a rocket, and then it starts declining, and you can see that here. So it's going up and down, up and down. And anyways, that's what it's doing here. But you could imagine the maser is kind of getting, so the maser is getting brighter, it's doing this, and then as it gets brighter, it starts getting broader too, because it starts to saturate. The cloud itself gets so hot, it starts to thermalize, and when it thermalizes, you cannot have a maser action, so it starts becoming linear. So it goes from viral, exponential, to linear, the growth. And when that happens, then the wings of the maser start getting brighter. And that's all it is. And for those of you in the science field, you'll know what the hell I'm talking about. For those of you who don't worry about it. It's not a train smash. But it basically tells us something about what the gas is doing. Okay? So, and then here's examples of all this, and I've got different features in different colors, and they're acting differently. So that's the interesting part here. In this particular in this particular graph, they're acting differently. So you got the very bright feature, which is the 1.2, the blue, and it has this quick rise and a long tail. Looks very much like it's following the path of its flux, its actual maser strength, whereas the others are doing different things. They look like they're falling. So they look like from the peak they're starting to rise, so they're opposite. So they're almost doing a bunny hop. And that's kind of bizarre. Okay, that's really bizarre. So that's a part of this crazy science, whatever the hell I'm talking about here, okay? Just to give you some idea. And again, I go through lots of this stuff. You can see the fluxes again. I'm trying to compare to see if they do the same business. And here's what I call let's make it bigger so you can see it better. This is what I call the flare cycle. And so in effect, what I'm saying here, going through one of the flares itself, as the flux gets brighter, this is and this is the way that goes. So the flare is increasing, and then it starts declining, and it doesn't just go back and forth. It shouldn't look like this. It should really just sort of follow its own path back and forth, the line width versus its flux. So this is what I call a flare cycle. Now the problem with this, and this is where the crazy part comes in, this is why it's just so weird, okay, is what the hell does this really mean? Okay, is it real, actually? Let's ask that question. Is it real? And the answer is, I have no clue. I have no clue. Is this real? I don't know. Okay? So this could just be an artifact of the flaring and the various features flaring. Remember, I have a single dish telescope in which I'm seeing, what's the word I'm looking for here? I'm seeing a velocity extent, okay, which represents a feature on my in my spectrum. The spectrum itself is comprised of many, many, many spots, maser spots, and each of them has slightly different velocities, and they blend, and they kind of look like your hand like this. So if one varies, the shape of the total power spectrum has changed, and that shape can affect this graph. So if I have variation going on, and if I have periodicity, and then there's a time lag between two of the features, so this one gets weaker, and then this one gets weaker, and then that one gets brighter, and it's doing something like that, it'll cause this to do weird things. So you got to be able to disentangle all this business. And it ain't easy. And quite honestly, I haven't figured it out yet. So, and then, like I said, you got to ask yourself, is it believable? Well, sometimes it's not. So that is what I call the saturation cycle. I've not published this. This is clearly new data. You're seeing this for the first time. I've asked people about it, some of my friends, and I probably will publish this eventually. But I have to convince myself that what I'm looking at is real. Okay? I have to convince myself of that, because single dish, you have all of these different features interfering with each other. So you really have to find a feature which is very much isolated from everything else, which you can actually clearly see this kind of business. Okay, so let's make it a little smaller. Now I'm doing different transitions. Let's see if I can find something else of interest here. Yeah, it's just terrible. Yeah, it's terrible. You can see all sorts of crazy stuff here. Where's my graph? Where's the one I want to show you? So again, and okay, so here's an example of what I'm doing. Let's make this bigger. Really, it's a pain in the ass. Right, so again, here we're looking at a nice graph, and I say this for the 1,000th time, if you're not a science person, I'm sorry. This is as pretty as my data gets. I don't have pretty pictures of the night sky where you see Andromeda galaxy spinning in the distance millions of light years away, or you got the Orion Nebula with all these beautiful structures and colors, and I don't see any of that garbage. I see none of it. This is what I look at all day. This is the astronomer's existence. The vast majority of us will spend our life looking at graphs. We won't be looking at pretty pictures. The day of the photographic plate and looking at them for hours and hours has largely vanished. Okay? In radio astronomy, you do get, if you do interferometry, of course, you'll get graphs that look kind of like a map that you find if you're looking for places, and in it you'll see maser spots or clusters, and then you can make pretty colors out of that, and it can look quite pretty. But this is not that. Okay? So you can imagine. Let me show you something here. Let's just go back to something here. Let me go back to the actual data. Just want to give you an idea. This is the data. Okay? Where the hell's my thing? There it is there. This is the data. That's epoch 1059 on May 1st. Epoch 1059. So that means that the telescope at Hart-Trail has looked at this source on 1059 days over the course of, let's go back to the beginning. Here it's to August 2003. Okay? Now you got to understand that from 1999 to 2003, I have more data of this source, which I don't include in this particular graph or this stuff, right? So it also exists. So I have another, 300. So I have something like close to 1,400 spectra. And this is what I look at. This is what I actually see as an astronomer. I see data all day. For those of you who think that it's somehow romantic to be an astronomer, let me assuage you of that notion. let me convey to you the simple reality that astronomy is exciting to astronomers, okay? And we try to wrap it into something that we can make presentable to you, the general public, and say, so that you will go, wow, ain't that cool? Well, we radio astronomers are really freaking bad at it, okay? We're really bad at it. We're not good. And so in the end, it becomes our personalities which sells the romanticism of it, rather than simply our data. Because to the average person, to my parents, to my brothers, they just look at me with a blank face and they go, what the hell do I care? And they'd say, bring me some mortar. I want another stone. You know, they don't give a damn. When I would return home from South Africa, while collecting this kind of data, I would get off an airplane and then get on a bus and get to the nearest city where they would come and pick me up and take me straight to the job site to start working. So I had to go, you know, you think you're sitting at airports and on planes discussing your science with someone beside you who might be interested, or whatever it might be. Maybe they're just bored for 20 hours like I am, and we'll talk about various different things. And then I'll get home, and I have to go to the job site and mix mortar and carry stone for my brothers. Okay? So that's their interest in astronomy, and that's the general interest that I get from when I talk about this stuff. But the reality is, astronomy is kind of cool, and you do kind of find some cool things. And from it, we kind of understand ourselves. I must tell you, a lot of this is really giving me a lot of introspection as to how I see myself in the world. So I kind of see looking up at the stars, in this case, things in the sky which you can't see. And I see it as looking at a mirror. And you're sort of looking back at yourself and you're asking yourself, you know, what are you? What is humanity? What are you? What are you personally? Because remember, in the end, you know, we're not humanity. We're just ourselves, right? We're just a guy sitting in a chair in front of a computer talking to a camera. And you know, there's very little more to that. Okay, so, but that is astronomy in a nutshell, really, is what are you? And that's what we're doing, right? And so sometimes we find some interesting things that helps us to better understand our place in the universe, or how we fit in, how the universe works. And that's a part of our place in it, right? And when you see graphs like this, well, you know, it's almost inexplicable to people. I like it because it has this kind of undulation to it, right? So, and of course, that's the periodicity. So in the red is the line width. That's W. That's line width, okay? So the width of my maser in velocity is these numbers here, from plus 0.31 to plus 0.35. And as the flare progresses, okay, as the flare progresses, you can see the line width is increasing, as I told you, and then it starts decreasing as afterwards. So the black lines represent when the flare reached peak flux. And so the line width didn't reach its maximum until after peak flux. That's what it's telling us, okay? That's the idea. So there's a slight delay. So all of this tells us something about how this stuff works, okay? And the beautiful thing about masers is we have no goddamn clue. We actually have this tool, which we use to probe star forming regions, because it's very easy to measure a 7,000 Jansky source as opposed to measuring a 1 milli Jansky source, which is 1,000,000 times weaker in the continuum aspect of it. So if I want to look at the continuum flux from this particular source, it's 1,000,000 times weaker than this maser, 1,000,000 times weaker. And so you have to use incredibly powerful telescopes like the VLA in New Mexico, USA, or the EVN in Europe. Basically, they're interferometers, effectively. Merlin in England, the Japanese system, the Australians, the Chinese. There's various other facilities that you can use. One day, Meerkat and SKA will join those ranks. Meerkat's already operational, but can't do this frequency. So basically, we're looking at something where something is happening to the gas, as the star is getting brighter. So we don't even know what's causing the pulsation. There's arguments. Some people think it's the binary winds interacting. Others think it's the star pulsing. Others think it's density waves traveling around the disk of the star forming region. So a big gas cloud is collapsing to form a star, and it flattens and it gives us sort of a thick disk, which is also rotating. Okay, and these masers, the velocity that we're seeing from them, which is basically here on the side in green. This is a really ugly color, just as a matter of course, but never mind. And so that represents sort of the rotational velocity predominantly of what the maser is. So somewhere in the structure of that disk, the maser resides, and it sort of reflects all the motions of that maser cloud, and most of that will be the rotation around the star forming region. And part of that, and it could be infall or outflow and all sorts of other things, and they'll all contribute some component to the velocity itself. So even the velocity, we're not 100%. Okay? So you're looking at a graph, which I think is real, but I can't even tell you what the hell I'm looking at. So I can explain to you what the axes are. This is time, this is line width, this is velocity, and I'm plotting my data set against this, okay? I can do all that, but I can't actually tell you what the hell's causing it. And that's the beautiful part of science. And that's the part I like. I will park off somewhere in the sun, relaxing at the beach or something like that, and I'll just be thinking about this graph. I'll just think about this particular graph, okay? Or I'll think of other graphs. But this is an interesting one, right? So if I look at this graph, what do I see? The quote-unquote astronomer amongst us, okay? Because we're all astronomers. The moment you look up at the night sky, you too are an astronomer, just so you know. Okay? So here we are. As I said, the line width gets to its brightest, the line width gets to its broadest after the flux gets to its strongest. So that's telling us something about the gas, all right? So it's probably telling us something about, and okay, let me stop. Let's assume that everything in here is real and not an artifact of my data analysis, of my Gaussian fitting, all those kinds of things. Let's assume it is, okay? And let's assume for a moment, which is totally wrong, but let's assume we're only looking at a single maser spot that we're trying to analyze, okay? So in other words, we're looking at a single cloud that's producing this maser, okay? And all of those assumptions are not good, okay? So they are very bad. They are very bad assumptions, just so you know, right? So they're not very good at all. I take these glasses, they drive me nuts. Anyways, so let's assume all those things. And for a moment, let's just assume that what we're looking at is real, and now we got to try to explain it. So I think I can pretty easily explain what's going on in terms of the line width as opposed to flux. So that's the saturation cycle. That would be my naive explanation of the whole story, okay? It's the saturation cycle. That's what I would think. And of course, the velocity is simply the changing shape of the, that's the word I'm looking for here, of the total power spectrum. So that spectrum, as I said, if you've got 4 fingers and one of them turns off, the velocity will shift this way. That was a bird hitting the window, just so you know. That noise was not me doing anything crazy. So if this turns on, the velocity then shifts slightly back towards the figure that turned on. And so if you're seeing multiple masers and they're all varying in unison, they'll do this. And then that shouldn't be occurring, okay? So basically, if there's some sort of time lag, it'll be all sorts of weird stuff happening. So you got to disentangle. But again, you got to believe that all of that stuff is what you're saying here. Now, okay, so one of the first things I can say to you is this, is that here you can see it's 1.22 to 1.2. So that's, okay, so that means that's a distance of 20 kilometers, 0.02 kilometers per second, which is 20 meters per second, okay? Now that's getting down to the level of the planets. And we don't correct for the planets in the VLSR at Hart Trail. In other words, I've got to correct for the motion of the planets, the impact they have on the sun and the earth and the observatory in this correction, which I have not done. So there I've already injected something that's going to cause some problems. But none of that can cause a 240-day period, which is basically the same as the line width and the flux, okay? So the period's real. So how the velocity changes in terms of the period is real. But you will see inside this data, you get little blips, like there's one here, there's one there, there's one, and there's one over here. And that could be simply something due to the planets or the Earth's eccentricity, just so you know. So I'm not going to read much more into that. I'm just looking at this in terms of, the line width versus the flux. And so the line width and the flux, they reach their maximum at almost the same time. So you can see here it's 75.80, and up there it's 75.79. So basically it's the same day. I mean, the error in this stuff will be plus minus. I think the observations here is every 10 days, so you could imagine. So it's every 5 days. So basically I'm telling you that the 7093 versus 7094. Yeah. So the velocity reaches its maximum motion, whatever it's doing, at the same time the line width reaches its maximum width. Just so you give an idea, okay? So in effect, the line width is blue shifting, right? So if you go to more smaller numbers, that means it's moving towards us. So the velocities, the object is moving towards us. This is basically Doppler shift, okay? So think of a train coming towards you and it's blowing its whistle. The whistle sound becomes more and more shrill. And then as it's moving away, it gets a lower and lower and lower tone, right? That's just the frequency that's the waves being spread out. And that's called Doppler shift. Well, that's what we're seeing here. So anyways, long story, cut it very short. I see lots of little things in here. Most of that may be the result of, for example, the actual drifting of the maser. This drift could be the result of the planets. I'm not certain, because Jupiter will cause a velocity drift of 12.5 meters per second. So that's basically, this is right here, that's 20 meters, that's 10 meters. So Jupiter can cause a lot of problems, right? So when I look at this data if I actually, let's see if I can do this. Let's just do this. Axis. Let me go back to, let's make it day, what the hell is this? Let's make it 1050. Is that right? Yeah. Let's do that. Okay. So, yeah. Okay, that's good. It's going to be messy, but let's do this. Okay, let's get out of there. It's got all sorts of weird shit going on in it. Pardon my French. Oh, sorry. Hold on here. Hold on. Talk. Took, I'm live streaming. You are now on my live stream. You are now on my live stream. So I'm talking while you're talking. Just so you know.
Hot chick 99.
Yeah. You'll be heard saying that. Okay, let me call you right back. I'm almost done here, okay?
Now, shall I tell you about AstraZeneca causing rare blood clots?
Yeah, okay, but let's not have the politics discussion while I'm live streaming. Girl. Okay, that's a friend of mine in South Africa, and she's going to be mad at me for even talking about that. But there it is. Okay. So, but the point is here you can actually see the planets. This is not real motion. This is not real motion. That velocity drift, the green is velocity, as I said. So that velocity drift is the result of me not properly correcting the VLSR. This is the VLSR. I call it V6.7, but it should be VLSR. Okay? So I don't correct it properly, and as a result, you can see the motion of Jupiter in this, and Saturn, to be honest with you, because they're the two major players in that. And then inside those, every 365 days, you'll see the Earth's eccentricity will cause something like a meter or two. So remember, this is 20 meters plus minus 16. So 1 or 2 meters will be a dip, and that's kind of what's happening there. So you can see the Earth's eccentricity. We're not perfectly circular going around the sun. Okay? And you can see this is Jupiter, Saturn causing this motion. Right? But none of that explains the periodicity in the actual velocity drift, which appears to be the same as the flux and the line width. Okay? So none of that explains that. So this is very real. This periodicity in the velocity of 240 days is very real. It's obviously the result of the source. I first have to subtract out the motion of the planets and their impact on my data set before I can publish this. Okay? So that actually shows you very quickly when we're getting down to that level of accuracy. Okay? You're literally getting down to the level of accuracy. In this case, we're getting down to of the order of meters per second. And when you're down at meters per second, you basically are now being able to see things which you probably couldn't see before. Okay, well, I know that. I know this for a fact. And so what happens in astronomy, and this is where I'm going to stop this. I'm going to leave it at this image, and I'm going to basically wrap this thing up. This really is crazy science, okay? This really is crazy science. This is at the edge. So I don't know if the saturation cycle is real. I don't know for sure. I got to prove that, okay? I would have to put that past peer review journals and stuff like that for them to say, yes, Gordon, that's reasonable. Your data shows it. Whatever. But I have other explanations that may refute it. So even myself looking at it, I'm saying, well, it could just be the result of time lags and things like that. Okay? And then here I can see the planets, the effect of the planets in my data. So if, for example, planet X was between Saturn and Jupiter and it was fairly strong, I would actually see it in this data. But of course, it's not. It's very far out in our solar system. And so this would give us a way to actually study, if we wanted to do that. We could be stupid, but we could do that. We could actually study the motion of the planets by using masers. But again, why would you do that? There's better ways. But we're getting down to accuracies of the order of a meter a second. Okay? And with that kind of accuracy, we can start seeing phenomena occurring. And that phenomena will be beyond simply seeing the planets. We will see things like the motions of the maser itself, or how its structure might be evolving. We'll see gain. Competitive gain. So in a cloud, the conditions are just right for this particular velocity, 1.22 kilometers per second. But as the cloud conditions change, the competitive gain will actually change this velocity to something different. Okay? And that change will be very small. But every time there's a flare, every time this source goes to 7,000 Janskis and then falls back down, it's injecting energy into the maser cloudlet, the cloud where the maser is forming or is formed, okay? And when you do that, it must cause variation. It must cause, and I mean variation to the what's the word I'm looking for? God, my lips are, these are rented lips. I have to take them back. But it'll cause variation to the composition there. Jesus, stupid word. It'll cause variations to the composition. So what'll happen is you're injecting energy into the cloud. It gets warmer. It means that the masers have a larger heat sink, which means that they get more energized, which means you have more photons, which leads to brighter masers. That's the first thing. But also what it's doing is it's causing ice crystals in there to disassociate. So you're sputtering molecules off the ice crystal surface, and you're also evaporating the ice crystal. So you're changing the chemical composition of the cloudlet itself. And then when the flare dies away, during the relaxation time, a lot of that will go back to its present state. Okay, but it will never go exactly back to the exact state. And that is probably one of the reasons, and this is what I'm trying to get at here. So if we see this and we think this is reasonable, we know that there's the planets causing that, but we know the velocity drift in the period of 240 days has to be something to do with the actual source. Now it could be something to do with line blending. And so it can be my spectra, how I'm measuring. So that, again, too, could just be a time lag issue, right? So, maybe another feature that's very close is turning on slightly separate. We don't see a lot of those time lags. I showed you that earlier. So that may not be the case. And the line width, maybe that's all real. But, so as I said, and here you can see the planets. There it is. There's a nice view. And there's the old data. And the old data from the old receiver that Hartrell had is not the same. The velocity is different, and that's because of the way the spectrometer was set up. So I would have to adjust this to match up with this data here. So that point there has to touch somewhere down here. So the data will then go sort of like this, like that, and then go down, drop down. And by the way, if I look at that, this drift, I will also see a linear drift here. And that linear drift is likely real. It's likely something to do with all those other sources which are drifting at more than a single channel. In other words, they're drifting, my velocity drift paper I talked about, the masers are drifting away from the neutral velocity, whether it's red shifting or blue shifting, okay? And so this source features also drifting a small amount, but it is drifting because I can see it in the shape of the planet motion. These are very small, so that it should be, it's tilted away. So I can actually see the velocity drift, and that drift is real, okay? Because the drifts that are for the other features that are greater than one channel, which means they're 3 times greater than any impact the planets would have on it. So that makes that drift real. So the publication I did before on velocity drift, I have to correct for this, but the reality is in the other data set, as you're seeing here, it's actually shown in this. And when I did a linear regression fit, it'll fit through all this data, and it'll take that into consideration, and it'll still be reasonably correct, at least for that particular one. There's another source feature that I'm getting very accurate numbers for. I have to make corrections. Anyways, and so there you can see the planets, as I said. That's the impact of the planets, but you got to fix for that. And that error there is the result of the actual spectrometer. Now, there's other problems that could happen instrumentally, and that's injected in here. And it can be that the spectrometer itself is calibrated in such a way that it's stretching the velocities. In other words, it's not analyzing the spectra exactly as the new one is. So that can actually cause, that distortion can cause problems when I'm trying to fit the 2 data sets, okay? And that's something I'm going to do in another paper, but it's painful. It really is painful. But it's life. When your technology gets better, you change out the old technology, you kind of hope the 2 will go forward and mesh each other. The answer is no, they don't. So as I said, here's the velocity drift. What was I looking for? What was I going to show you? I was going to show you that, where is it? No. Let's see if I can find those things. And again, you can see them here. There, you can see it nicely there. So it looks different, right? Because now this spun is brighter than the other one I showed you a moment ago, and that's because the velocity drift is the other way. Just so you give an idea. Okay, but what I wanted to get to, where is it? I just want to go back. Yeah, here it is here. Okay, here it is here. So remember what I was telling you, that I can't tell if this is real or not, right? So I know the velocity drift is periodic with the flaring of the maser. Okay, I know that for a fact. I know the line width is periodic with the maser flaring. I know that for a fact. I don't know if the results of some of them are caused by instrumental issues. Certainly not by the old receiver. I'm looking at the new receiver data predominantly. So this whole progression could be the result of just time lags in the masers. But what I might, if it is real, then what I'm looking for is, are they always the same? And you can see here, 2 different flares, they look different. So what does that tell us about the composition of the maser cloudlet? We're now actually studying the maser cloudlet. A lot of people, remember, we use these things, what am I saying remember for? People use these things as probes into star-forming regions. They want to look at how a star is being born. I'm saying, what's happening to the maser? Is the maser moving? When people do proper motion studies, the maser is moving. Why do they do those studies? Because they want to understand the dynamics of a star-forming region. Again, they're using it as a probe. They're not that interested in the maser itself. Okay? The maser is just a probe for them. It's the Swiss Army knife of star-forming regions, especially massive star-forming regions. Okay? Masers are the Swiss Army knife of massive star-forming regions. We can use it as a screwdriver, a knife, whatever, a file, whatever. And so in this case, people can look at the motion of the stars by measuring the motion of the Masers, okay? And because they're so bright, they're so easily recognizable. That's why. And what I'm saying here now is I'm no longer looking at the star formation, the star forming region. I don't care. I'm looking at the cloud of where the maser is. So now I'm trying to understand how the cloud actually functions, the cloud where the maser resides. So I'm actually studying the maser, not the star forming region. And there's a difference, okay? And here, if all the other stuff, if I naively assume everything is real, none of the other stuff is a problem, then what it tells me is I'm seeing variations in the cloud as different flares occur. So there's flare 31. I haven't got the lines on it, but they are operating kind of similarly. So it looks like the star forming region, or the cloudlet rather, the maser cloudlet, is going through a saturation cycle which is largely repeating itself. And over time, does it vary? Does it change? Well, that's what you want to know. You know? So, I mean, here's another one for another feature. So you're seeing it doing something, right? Anyways, and so I'm going to leave with that. This is the crazy part of what science is. We look at these images. To me, they're beautiful. To you, they're just weird graphs. Okay? And what we're trying to understand here is the maser cloudlet varying? Are we seeing something changing in the maser cloudlet? Now, we're beginning to get to that stage with other things where we're studying the snow line. It's where gases start, filtering out of the gas. They actually go to the solid state phase, right? So they go from gas phase to solid phase. And that's the snow line, okay? And now I talked about that earlier when I talked about a molecule is sputtering off of a dirty ice ball. So there's little tiny grains of carbon in that, and then on it there's a methanol molecule. And when it gets enough energy, when the grain absorbs an infrared photon, it causes the surface to get energized, and the molecules actually pop off and they become a gas. They go from solid phase to gas phase and vice versa. Well, are we not seeing this here? I don't know. So this is the end result of this. So anyways, I'm going to stop it there. Science can be crazy. As I said, astronomers, really in the end, I make graphs. This is as pretty a graph as I can make you. This is as unique and as pretty a graph I can make for you. I'm doing it in Excel. It's not earth-shattering in any way, shape, or form, at least for the vast majority. I mean, literally, there will be 100 people on the planet interested in this graph. Okay? 100 people. The rest of the planet, all 10 billion of you, will go, who the hell cares? And rightly so, because it don't feed me. I got to get up. I got to go do some work. And that's what I'm going to do now. I got to get up. I got to go do some work because I got to pay my bills. Okay? So let me do that. But thank you for watching this. I have a scanned, you can see the scan image like that. If you want to go and scan, you can scan, go to our website, and of course this will be posted to the Jira channel videos, okay? So wherever you are in the world, keep looking up. Happy observing.